Section 3.5, Implicit Differentiation. This is going to use the chain rule that we just learned to essentially start getting some derivatives of equations that aren't even functions. So almost all functions that we've considered are given explicitly as y in terms of x. So things like y equal x squared or y equal cosine x, etc. And we've needed things to be in that sort of function notation to then find derivatives. But there are some relations that are not given as y in terms of x, such as x squared plus y squared equals 25, or even something else like x cubed plus y cubed equals 6xy. In fact, both of those aren't even functions of x, as you're going to see. The first one, x squared plus y squared equals 25, that is a circle centered at the origin with radius 5, which means it wouldn't pass the vertical line test. The second one we'll see a graph of in a little bit. But if we wanted to get a function y equal f of x for the first equation, x squared plus y squared equals 25, we'd have to solve for y and then get two different functions. Y equal plus or minus the square root of 25 minus x squared. Both of those make the whole circle, but individually they are the upper and lower halves of the circle. From one of those, we could then get the derivative dy dx. But the other relationship that we have, we can't easily do that. Trying to get y by itself with x cubed plus y cubed equals 6y, that would be a very difficult thing to do, to try to get y by itself. And this is an important point. We don't want to be stopped by that so that we can't find the derivative. We need something else so that we could still find dy dx for even things that aren't given in that explicit form of y equal a function of x. Because, for example, what if we wanted to find the slope of the line that is tangent to the curve defined by either of those equations at some point? We've only known how to do that when we have y all by itself. So what we're going to do is take a look at that second function, or second expression, I should say. And instead of writing it as x cubed plus y cubed equals 6xy, we're going to replace y with f of x. Because we can still think y as the dependent variable is a function of x, the independent variable. So we write x cubed plus f of x cubed equals 6x f of x. Then, when we want to take the derivative, we're going to use the same rules that we had before. Product rule, quotient rule, chain rule, all of those things. And the most important of those is the chain rule. So, in this first example, find y prime if x cubed plus y cubed is equal to 6xy. So for this, let's just rewrite as we had up there. X cubed plus f of x cubed equal 6x f of x. So now what we are going to do is take the derivative of everything with respect to x. So the derivative with respect to x of the left-hand side, and the derivative with respect to x of the right-hand side. Right here we're going to have some rules that we can use. On the left-hand side, we have a sum, which means we can distribute the derivative across that sum. So the derivative with respect to x of x cubed plus the derivative with respect to x of f of x cubed. And then on the right-hand side, we need the product rule, which means we have to take the derivative with respect to x of the first part of the product, which would be 6x, and then multiply that just by the second function, f of x, and then we add the derivative with respect to x of the second function, so the derivative of f of x, and then we multiply that by the first function. Now we can start finishing this up. The derivative with respect to x of x cubed, that's 3x squared. The derivative with respect to x of f of x cubed, this is where we need the chain rule. We have an inside function, f of x, and an outside function, which is the third power. So something to the third power. So we use the power rule for that derivative, which would be 3 times the inside function raised to 1 less power, 2. And then we need to multiply by the derivative of the inside function. And all we have for this is just notation. The derivative with respect to x of f of x. That is f prime of x. And then on the right-hand side, the derivative with respect to x of 6x is 6. And then the derivative with respect to x of f of x, again, notationally, that's just f prime of x. All we've done is just take the derivative with respect to x of f of x, that clunky notation, and just replaced it with f prime of x, something we've already seen before. So now if you notice, you have f prime of x, which is the same thing as y prime. So really all we have to do is just get that all by itself. So then this just comes down to reorganizing some terms. So I'm going to bring the things that have f prime of x attached to it over to the left, which means I have 3 times f of x squared times f prime of x. That was already on the left-hand side, and I'll bring what's on the right, f prime of x times 6x, I'll bring that over to the left by subtraction. And then on the right-hand side, I had 6 f of x, and then I have to subtract 3x squared. And now you can see that we can just clean this up by factoring on the left f prime of x. What's left from what I factored out from would be 3 f of x squared minus 6x. And then on the right, 6 f of x minus 3x squared. So then to get the derivative all by itself, I just use division. So that means I have the right-hand side, 6 f of x minus 3x squared, divided by what was in that square brackets, 3 parentheses f of x squared minus 6x. And so to finish this, instead of writing f of x or f prime of x, we can just use y or y prime. And then you can also notice that in my fraction, in every single term, there's a common factor of 3. So I'm going to divide each term by 3. So this means I just have y prime equal 6 divided by 3 is 2. Instead of f of x, y minus 3x squared divided by 3 would be just negative x squared. And then in the denominator, again, 3 divided by 3 is 1, and I'll replace f of x with y, so that's y squared, and then minus 2x. So that's our derivative. What was next, part B, find the tangent to the graph of that equation x cubed plus y cubed equals 6xy at the point 3, 3. So we already have a point, so all we need is the slope, and then we can use the point slope form. We have an expression for the derivative, so for part B, the slope is y prime evaluated at the x value 3. So I'm using the x value of 3 in that derivative. That's how we find slope. We always use the derivative evaluated at an x value. But we also notice that our derivative has y values. So we actually need a little bit more. We're going to evaluate this at the x value 3, and we do need the y value of 3 also. So then plugging that in, wherever I have a y or an x, it gets replaced with 3. So I have 2 times 3 minus 3 squared, and then y squared, so 3 squared minus 2 times 3. That gives me 6 minus 9, or negative 3, divided by 9 minus 6, which is positive 3, so that's negative 1. So then my equation would be y minus 3 equal negative 1 times x minus 3. That's using the point slope form. And if we write this in slope-intercept form, that would be y equal negative x, and this will be plus 6. So now I just want to look at a graph so we can see what we did here. So first, we need to see a graph of that original expression, x cubed plus y cubed equals 6xy. So over on Desmos, I have that graphed. X cubed plus y cubed equals 6xy. I also have the point 33 labeled there. So you can see here, this does not pass the vertical line test. So that's what we needed, this new way of finding the derivative. That's not a function. And then our tangent line, we said was y equal negative x plus 6. And if we plot that and show its graph, you can see it intersects the red graph at the point 3, 3. And you can see that it's just touching it once at that point. So that's the tangent line to that graph at the point 3, 3. All right. So that's it. That's the process of implicit differentiation. The idea of the word implicit is that the expression is not given explicitly as a function of x. It's implied. And what's implied is that y is a function of x. So all we are really doing is using the chain rule and incorporating f prime of x or y prime as a placeholder for that derivative that we're trying to find. So let's try this out with a couple other examples. Next example, find dy dx or y prime by implicit differentiation for tangent of x minus y equal to y divided by 1 plus x squared. So all you can see is we're just having some fun with all of our derivative rules and using the chain rule whenever we need to have something for y prime or dy dx. So again, we're just going to take the derivative with respect to x on both sides. On the left-hand side, we're going to need the chain rule. The derivative with respect to x first of the outside function. The derivative of tangent is secant squared, but that has to be evaluated at the same place that tangent was, so x minus y. And then by the chain rule, we now need to find the derivative with respect to x of what's inside x minus y. On the right-hand side, we use the quotient rule, which means we need the derivative of the numerator first. And the derivative with respect to x of y, we've been writing as y prime. So I'll just do that now. And then we multiply that by the function that's in the denominator, 1 plus x squared. And then we subtract the derivative with respect to x of the denominator. The derivative of 1 plus x squared, the derivative of 1 is 0. The derivative of x squared is 2x. That's the derivative of the denominator, and then we have to multiply that by the numerator. And then we divide this by the denominator squared. So now going back to the left-hand side, we have the derivative with respect to x of x minus y. The derivative of x is just 1, and the derivative of y is just y prime. And then on the right-hand side, we've got y prime times 1 plus x squared minus 2xy divided by 1 plus x squared squared. So all that would be left to do is just to simplify and get y prime by itself. And you can see this would just take distributing on the left-hand side and then probably splitting up that fraction on the right-hand side. So we know that we can do that. Sometimes you don't really even need to. So for now, we're just going to leave it like that. If you want to try to rearrange some things and check what you got, go right ahead. But let's move on to the next one. Find y double prime, or the second derivative, by implicit differentiation, if x cubed minus y cubed is equal to 7. So again, take the derivative with respect to x of the left-hand side, and then we need to take the derivative with respect to x of the right-hand side. So on the left, we'll distribute the derivative. So the derivative with respect to x of x cubed is 3x squared. The derivative of y cubed with respect to x would be 3y squared. But then here, again, we need the chain rule. We have to take the derivative of the inside function, which means y prime. And then the right-hand side, that's just a constant, and the derivative with respect to x of a constant is 0. So to get y prime all by itself, we can subtract 3x squared from both sides and then divide by negative 3y squared, and we would get x squared over y squared. And since we're going to be needing to find the second derivative, it might actually be helpful if we just write the first derivative as a product, since the product rule is a little easier than the quotient rule. So for the second derivative, we're just going to use the product rule. So the derivative of the first function, x squared, that's 2x, and then multiply by the second function, y to the negative 2. And then the derivative for the second half of the product rule of the second function would be negative 2 y to the negative 3, but then times the derivative of y, which is y prime. And then we have to multiply that by the first function, x squared. And you can see here we have y prime, which we have an expression for back where we left off. So we can actually plug that in here. So cleaning things up a little bit, instead of writing plus negative 2, I just have minus 2 y to the negative 3, and then y prime we have an expression for, that's x squared over y squared, and then we have that this is being multiplied by x squared. So then finally we can use some properties of exponents to write our final answer. Minus 2, the x's combine to be x to the 4th, and then the y's, y to the negative 3 divided by y squared is y to the negative 5. And so that's our answer for the second derivative. All right, so finally, we can use this whole process to get derivatives of some more functions. So if you're keeping track, we've seen derivatives of polynomials, rational functions, exponential functions, trigonometric functions. Now we have the inverse trigonometric functions, and the very next section we're going to see derivatives of logarithmic functions, which is pretty much taking care of all of the functions that we ever learned in pre-calculus. So for the derivatives of inverse trig functions, let's start with looking at y equal the inverse sine of x, or arc sine of x. We can find the derivative by doing some clever manipulation. Using the definition of the inverse function, we can write sine y equal to x, because anytime that you have y equal to sine inverse x, it means the exact same thing as sine of y is equal to x. That's how inverse functions work. They're just undoing the other function. So we're going to take that expression, sine y equal x, and differentiate with respect to x on both sides, just like we were doing above in those previous examples. So the derivative with respect to x of sine y, that's just the derivative of the outside function. That gives us cosine, evaluated at the inside, y, and then times the derivative of the inside function, which is dy dx. And then the right-hand side, the derivative with respect to x of x is just 1. And then if we use division, we get the derivative with respect to x is just equal to 1 divided by cosine y. But we don't want to just leave it like that, because we would like the derivative to hopefully maybe just be expressed in terms of x. So what we're going to do is draw a triangle in quadrant 1 that relates to sine y equal to x. This means that the sine of the angle y, which would be here, is equal to x. The sine function relates to opposite over hypotenuse. So that means that the vertical side, which is opposite the angle y, is x. And then x divided by 1 is x. That means that the hypotenuse has to be 1. And then by the Pythagorean theorem, the horizontal side would be the square root of 1 minus x squared. So that means that cosine y, which is adjacent over hypotenuse, is just the square root of 1 minus x squared. And so that tells us that the derivative with respect to x of sine inverse x, dy dx, because we had said that y is equal to sine inverse of x. So the derivative with respect to x of sine inverse x is 1 over, and instead of cosine y, the square root of 1 minus x squared. And that's it. In the exact same way, we can get all of the other derivatives of the inverse trig functions. And again, you'll notice some patterns here. What we have for the derivative of sine inverse looks an awful lot like what we have for the derivative of cosine inverse. It's just that they differ by a negative. And then if you see what we have for the derivative of tangent inverse of x, it's 1 over 1 plus x squared. But the derivative of the cofunction, cotangent inverse, that's negative 1 over 1 plus x squared. And then finally, the derivative with respect to x of secant inverse x is 1 over x times the square root of x squared minus 1. And then if you also look, the derivative with respect to x of cosecant inverse, that just has a negative 1. So it comes down to just remembering one of these, and then the cofunction just is negative.